So in the last class, we were looking at the transfer mechanisms, right? We had started with what are the transfer mechanisms, isn't it? Transfer mechanisms. Basically, two categories we can make: linear transfer and rotary transfer. So, as the name suggests, this is used for linearly transferring the work parts or assemblies, sub-assemblies, etc. And rotary transfer, as the name suggests, in a rotation fashion, right? Circular fashion. So we had seen walking beam system, right? We saw the video how this works. Basically consists of these transferring beam and fixed beams, right? The motion of this transfer beam to lift it up, move it to the right, and then place it down like that. So that was your linear transfer. And the powered roller, as we were discussing the last topic yesterday, these rollers are used to move the work parts. So it could be either through a belt, right? That you have a belt, flat moving belt, and beneath that those rollers, and because of the movement of the belt, right, and the friction between the belt and the roller moves. All the roller moves, and therefore it is able to move the work part. So that's one way of conveying parts, right? You can see those tires. So basically, this is used for bulky parts, as I said yesterday. Another thing is your chain drive conveyor system, right? Chain drive conveyor system, either a chain or a flexible steel belt is used to transport the work carriers. Chain is driven by pulleys either in an over and under configuration, right? Another one is around the corner. So basically, if you see, uh, yes, you see here, these are your two pulleys, right? That's your chain, and these are your work carriers. So forward travel. So as this rotates like this, the work carriers are being moved. Okay, they move forward. Now, and this is for return. So basically, once it returns, I mean, this is where the parts have been taken off. Okay, so this can now go under it, right? So that's why we call it over and under configuration, right? Over and under configuration. So basically, in here, in this, what do you call? While it is moving like this, there are no work carriers on these. I'm sorry, there are no work parts on these work carriers. You see, so over and under is this one, wherein the pulleys turn about a horizontal axis. So you see this axis, the axis is actually perpendicular to our screen, right? Normal to our screen. So if the pulley rotates about that axis, which is perpendicular to our screen, then you get this over and under configuration. If it is around a vertical axis, then what do you get? If I could draw, right? Like for example, you have this. This is the axis about which it is rotating. Okay, so you have a pulley. I'm drawing it 3D. Okay. Um, okay, that's your pulley. Okay, this is the axis about which it is rotating. Okay, so you'll get it like this, right? So if I could show you, like say, let's say this is one corner, that is another corner. So when it moves, it will take parts from here, right? This is the way it is, they are moving, right? Like that, and all the way through the pulley and like this. So that's why you call it around the corner, isn't it? So if it is around a vertical axis, then you get around the corner configuration, right? If it is horizontal, then you get over and under, isn't it? Is that clear? What we mean by over and under and uh, around the corner configuration, or are there any doubts? Clear, right? Okay, so you have those two kind of configurations. This general type of transfer system can be used for continuous, intermittent, or non-synchronous movement of work parts. So it can either be used for continuous, intermittent, or non. Basically, all types you can say, right? It's a general type of transfer system. That's why we are calling it general. In the non-synchronous motion, the work parts are pulled by friction or ride on an oil flame along a track with a chain or belt providing the movement. So, especially for non-synchronous, as we were saying, pulled by friction, right? That you don't have to, what do you call, place any other fixture or something to place it, to keep it on in place, right? They do it by friction. It's necessary to provide some sort of final location for the work parts when they arrive at the respective stations. So, as I said, it is also the responsibility of the this conveyor system to locate that. So, to final location also, I mean, they have to provide that for the work parts because they are basically carrying the work parts, right? So that coordination has to be there, basically by the driving system of the pulley, right? That will maintain that. So yes, I believe linear transfer system ends here. Okay, the last category was your this thing, and other thing I believe we should look. Mhm. Yes, we'll look at all the configurations. Okay, all the different types of mechanisms, both linear and rotatory, and then we'll look at a video. Okay, of the conveyor system. Okay, so when it comes to rotary transfer mechanisms, you have these several methods, some of which we are discussing. Okay, why are they used? To index a circular table or dial at various equal angular positions corresponding to workstation locations. So indexing is basically what is being done here, that you have to move the table, right, at so and so locations, right, with so and so angle. Every rotation, the work table moves at some angle. Okay, that's what is called indexing. Okay, to index a circular table or dial at various equal angular positions corresponding to workstation locations. So I believe we saw the diagram, right, earlier, of that rotary one, where I gave you the example of that, how this table is able to shift the work carriers or the work parts to the different processing stations, right? So it is here, okay, exactly here, below this table, that you will have that mechanism, the indexing mechanism. So that rotary, exactly here, that rotary type of automated flow line will utilize this rotary type of transfer mechanism. Okay, so several methods. One among that is your rack and pinion. Okay, mechanism is simple but not considered especially suited to the high speed operation often associated with indexing machines. So it is simple but not considered because of the high speed operation. So with the indexing machines you have to have that high speed, right? If you can see here, it's a very simple, right? We even, I believe you have seen this in your com subject, right? The steering, one of the steering mechanisms will use rack and pinion itself, right? So you have a rack here with the geared profile, and the same, what do you call, same addendum, basically we can say, just to be able to match it. You have this gear, okay, with the teeth and diameter ratio as equal to this, so that you can have a matching of it. So as this rotates, this rack moves linearly. So basically rotary motion to linear motion. So if you want to have a rotary motion of the work table, right, we saw that in the rotary configuration. If you want to have a rotary motion here, this rack will provide that. The movement of this rack will provide a rotary motion to this pinion, right? That's how we are able to get that mechanism of rotary mechanism. So this piston is what will drive that rack, and adjustable stop to limit angular distance index. So how much to move is this, we will have this stop, okay, so that it doesn't move more than what we desired it to. So this rack will only move until that stop, right? So we can have this indexing pinion driving table through unidirectional clutch. So only in one direction, right? That, for example, if the rack moves like this, right, then you see the rack will, if the rack moves like this, then the table will move as shown here in this diagram, right? This arrow, the pinion will move, and it has to come back, right? The rack has to come back to be able to again move it. So this is why we are having this unidirectional clutch. Okay, that will only move, that will only allow rotation in one direction, which is namely this. This is the rotation that will allow only this way, not this way. Okay, otherwise if the rack moves to the left, then the pinion will again move back, so there's no use, right? So unidirectional clutch, if you have seen in that ratchet we use, right, in uh, used by mechanics, right, that ratchet, if you have observed, it is also unidirectional, so it will only activate in one direction, like namely clockwise, let's say, and in anti-clockwise it will not operate, so it will allow it to move. I hope I'm clear, right, by what this mechanism intends to do and how it does it, right? So that's how it works. Okay, the device uses a piston to drive the rack, which causes the pinion gear and attached indexing table to rotate. A clutch or other device is used to provide rotation in the desired direction, as I explained, right? Unidirectional clutch will only permit the rotation of this table in one direction. So that's how you achieve rotary mechanism in using rack and pinion. Okay. Other thing is your ratchet and prawl. Okay, ratchet and prawl mechanism. So ratchet is a device. So basically, this is what I was talking about, right? For that clutch mechanism. Okay, don't confuse it. I was trying to explain the clutch mechanism by mentioning ratchet. Okay, so if you have this kind of mechanism, right, a ratchet is a device that allows the linear rotary motion in only one direction. So you imagine that ratchet, if you have seen a ratchet, uh, the inside mechanism is like this, right? So if you can observe here, the rotary motion of this pinion, let's call it, okay, is, you see those teeth, and if it moves this way, this what do you call link, okay, will move up, right? And if it tries to move the other way around, that is to say clockwise, okay, like this. So if this pinion tries to move like this in clockwise fashion, then it will not allow, so only allows in one direction. Okay, so ratchet and pawl is one type of mechanism to convert that, to have that rotary motion, allows a linear or rotary motion in only one direction while preventing motion in the opposite direction. A ratchet consists of a gear wheel and a pivoting spring loaded finger called a pawl. So that's what is called a pawl. Okay, the technical name for it is pawl. So that engages the teeth, right? And either the teeth or the pawl are slanted at an angle, so that when the teeth are moving in one direction, the pawl slides up and over each tooth in turn, with the spring forcing it back with a click into the depression before the next tooth. So if you have observed that ratchet that we use, it also makes a click sound. So that clicking sound is because of this. It is continuously striking the teeth, okay, on this ratchet is what we are calling it, right? Gear wheel. Gear wheel is what we are calling it. Gear wheel and pawl. Okay. So when it clicks, when this pawl clicks this gear wheel, then you have a click. So it clicks because it is striking it again and again. Okay. So when the teeth are moving in the other direction, the angle of the pawl causes it to catch against the tooth and stop further motion in that direction. So this is very simple, right? So when this piston, okay, is trying to move it, okay, this stable spindle will be integrated with this pawl. Okay. So just as we had in what do you call rack and pinion, that the table spindle was here, okay, attached to this pinion. So as the pinion moves, the table spindle also moves. So I had explained you that, right? That beneath that you have this mechanism, right? So movement of that pinion behind this table, right, below this table basically, will move this table. Okay, so you try to imagine it as one entity. That table spindle is attached to this table, right? So that's how we are able to convert this linear motion of the piston into rotary motion of the table spindle, right? So that we can move the work parts, right? Clear, right? Ratchet and Paul. And next one is your Geneva mechanism. That is also under your rotary transfer mechanisms. So two previous mechanisms convert a linear motion into rotary motion, right? That's what we saw. Ratchet and Paul and rack and pinion. They convert linear motion into rotational motion. Whereas the Geneva mechanism uses a continuously rotating driver to index the table. So I'll show you here. You see, this is a driver. Okay, it has a slot on it, right? You can see here. This is your driver. The green one is your driver, okay, and that red one is your driven member basically. So if the driven member okay, uses a continuously rotating driver, the driver is continuously rotating, okay, and as this driver comes into contact with the slot, okay, in the driven member, the driven member also moves. So the driver is continuously rotating, but the driven member only rotates when the pin on the driver engages with this slot on the driven member, right? I'll show you in the video. That will be very clear. So if the driven member has 6 slots for a 6-station dial indexing machine, each turn of the driver will cause the table to advance 1/6 of a turn, isn't it? So you see how this how there is a correlation between the number of slots and the stations on the machine. So if you have a 6-station dial indexing machine, basically if you observe that table, you see 1 2 3 4 5 6. You have a 6 here, right? So if you have these 6 machines, okay, this is irrespective of the starting and completed parts. Okay, we're not considering that. If we had to consider that, then we had to include 2 more machines here. Okay, so if so the number of slots on that driven member are decided by the number of stations you have. Okay, each slot, okay, movement of each slot will give you a movement of these work parts, right, from one station to the next. So that's how those slots are correlated. Okay, that's how the slots that you're seeing 1 2 3 4 5 6, right? 3 on the upper side and 3 on the lower side. So basically those are slots. So if there are 6 slots for a 6-station dynamic machine, each turn of the driver will cause the table to advance 1/6 of a turn, isn't it? 360 degrees is your total uh, movement to move, right? Total angle on in a circle, right? 360. So if there are 6 slots, if you divide it by 6, then 360 by 6 will give you what? 6. So that's 1/6 of a turn, isn't it? So the driver only causes movement of the table through a portion of its rotation. As I was telling you that the driver will continuously rotate, okay, 360 degrees, okay, but the movement of the table is only when the driver engages with the driven member. Okay, the movement of this driven member is only when the driver engages with it. So for a 6 rotor driven member, 120 degree of a complete rotation of the driver is used to index the table. The other 40 degrees is dual. So we'll explain that in you'll get it when we see the video. Okay, for a 4 slotted, just to give you an idea, okay, for a 4 slotted driven member, ratio would be 90 for index, right? 4 slotted 360 by 4 gets you 90. So each machine is at 90 degrees. So and 270 degree for dual. The usual number of indexings per revolution of the table is 4, 5, 6, and 8. So indexings per revolution of the table are generally this much. So depends on the number of, so the slots depend on these uh, indexings. Okay. So okay, that's what Geneva mechanisms looks like. Okay, we'll see a video on this, and then yes, we'll have a video. Okay, so I hope the screen is visible to you. Able to see the video, right? And also audio. Please confirm if you're able to hear the audio.
Conveyors move bulk material or discrete products from one area to another and
Yes or no? Yes, students, able to hear the audio and see the video. Okay, so we'll look at the Geneva mechanism first, okay, and then the conveyor system. Okay, the general, because it covers all categories. Okay, so you see Geneva mechanism. That's your animation. Clear, right? This is your work table. Basically your work table that you want to move will come here, okay, on top of this. So it is the rotation of this which is what we require, okay, and to get that we're using this driver, the the one on the left, okay. So you see there are 4 slots here, and when the driver is engaging in that slot, it is moving it 90 degrees, right? And so I hope this is clear, right? No doubts in this video. We have another video just to give you a uh, real video of that mechanism. You see those slots are placed, that slot is placed, I mean there's a recession there because you want to avoid the interference between these sharp edges on this driven member, right? Observe. So this is just he's manually rotating. When you use a, what do you call, motor attached to it using a belt, it'll be like this when it is running in speed. So it is with the help of this rotation that each workstation is being fed the work part, right? So that's how we are able to feed the work parts, okay. This is a mechanism for the reason why we want to have this rotation of the work table is because we want to serve or feed the parts to these workstations, right, which will be placed above this mechanism, right? So this is clear, right? Geneva mechanism. Okay, so we'll see this conveyor system here now, okay.
Material or discrete products from one area to another. Conveyors move bulk material or discrete products from one area to another and serve as main material handling arteries to improve efficiency and throughput. Advances in materials, controls, and modular subcomponents have spurred new large conveyors for bulk material transport, miniature conveyors for discrete sorting, and everything in between. During manufacture, myriad products move on conveyors. So conveyors come in an array of shapes and widths of less than 2 inches for moving extremely small parts to several feet wide. Once viewed as an afterthought, conveyors have become an integral element in nearly all automated facilities and applications. Select a conveyor first by asking, what types of product is the application moving? Conveyors for material handling of bulk product are more rugged than those for moving discrete product. In contrast, the latter requires conveyors that can advance product with more precision.
Right, before selecting a conveyor system, the questions that are to be asked is what is the type of product that you want to move, right? That is one factor in deciding what conveyor system to use. So if it is a bulk one, it'll be more rugged and it'll be heavy also, right? And it'll not be that precise, okay, uh, generally. But when it is moving discrete products, okay, as for example, if you want to exactly position it, right, the conveyor system has to be so designed that it is able to locate, okay, the work part exactly uh, to that what do you call transfer line, okay, or that spindle, machine spindle, because it is the uh, location of that work part. Okay, the responsibility of that also lies with your conveyor. So that's why you have this with more precision when it comes to discrete products if you want to move. But generally, if for example that tire we saw in the tire manufacturing industry, it was moved on that on those rollers, right? So that need not to be that precise, because we don't need that much precision there. It is for general movement from one department to the other, basically, right?
In contrast, the latter requires conveyors that can advance product with more precision. How does surrounding equipment interact with the product riding on the conveyor? Conveyor Class 1 includes material handling uses in which the conveyor serves as an artery to transport bulk or discrete product in a steady stream with little interaction along the way. Class 2 includes conveyors that act as bridges to take product from one location or machine to another. Class 3 includes conveyors that take materials into or out of machines or stations. Class 4 includes conveyors that run right through machinery without break. The first two classes generally prioritize ruggedness or throughput. The last two classes need positioning and, in many cases, custom workpiece pucks to steady product while machines perform work on the product pieces.
Right, the last one is your transfer line. Basically, they'll just run through the machine, right? In your transfer line, that in the slide I showed you, like 6 station, or was it 4 station transfer line, wherein you can see that the yellow work handling, automated material handling line was clearly seen. So it goes through the workstations, right? So that needs precise positioning, isn't it? That's what we're talking about. So that is the last category in here.
What is the maximum weight of the product being moved? Does the conveyor need to operate at a certain speed? Does the application need the conveyor system to have inclines, declines, or curves? Look for conveyor features that secure or enclose the material